So induced EMF is really seen best when working with loops of wire, or it's optimized when working with loops of wire. And that's because of the fact that you can have, like if you have a really long wire, that same length of wire can, just if you coiled it up, it can occupy much less space if you coil it up. And so it's a chance to expose this region with a magnetic field, whereas here if I only expose that region. So many of our applications that use this process of induced EMF will coil up the wire just so that we can have our changing magnetic field affect a larger amount of wire, which will create a larger current. Okay? And the whole process by which this is happening is something called Lenz's law. And so I'm going to kind of walk through this process. And so essentially the first thing that happens is that a changing magnetic field creates an electric field. So something is causing the magnetic field to change, like some external mechanism causes the magnetic field to change. If a wire is nearby, it will experience this new electric field. And then, kind of next step, is that this new electric field will cause charges in the wire to move. And just a couple things with this. Moving charges are just current, right? So moving charges is this, I'll say not is the same. We'll go math here. Moving charges is just current. And so this is an induced current is created. And oftentimes we associate this induced current with this induced EMF. In actuality, the current is what's induced, not a voltage or an EMF is induced. So an induced current is created, and then this induced current, so this is kind of like sets the next thing in motion. This induced current has its own magnetic field. So this is now a new secondary magnetic field. And little note about this induced magnetic field is in the opposite direction. I'm going to have to scroll up. It is in the opposite direction of the change in the initial magnetic field. And so this is really abstract. Okay, so let me just try to model this. Let's say I've got a region where I've got a whole bunch of magnetic field lines, and they're going like in this direction. Okay, I can visualize this huge magnetic field going that way. And let's say I've got like a loop of wire And so my original magnetic field is going inside my loop, and then something changes. So I go from this to looking like this now. Somehow, well, let me make this a little more drastic. Somehow, like, my magnetic field decreases, and I don't have anywhere near as many field lines going through that loop. So what happens is that because of this change, a current is created, or an electric field is created. So in this change, what happens is an E field is created. Electrons move. So electrons in the wire move. This new current causes a new magnetic field to oppose the change. So remember, my change is the fact that I don't have as many field lines, original field lines, right? This is my original field. And here's my loop of wire. So if I'm going to, essentially, I'm going backwards now. If I'm going to create new magnetic field lines to oppose the change, essentially what happens is I create new field lines. So these green guys right here, these are the new magnetic field lines. And they are created because I end up having this current that, oh, maybe can I go highlighter? I have this current that is like going around this loop of wire that is creating that new magnetic field line. So essentially kind of step by step again, in this case, I don't know if I can go here. In this case here, nope, you can't see that. But I don't want to like totally go crazy color here. In this case here, I have my original magnetic field. All of a sudden, my magnetic field decreases, so steps happen. My magnetic field decreases means I've got a changing magnetic field. The changing magnetic field creates an electric field. That electric field causes electrons to move. Electrons moving is just current. That current creates a new magnetic field that opposes the change. So I've created this current here that's creating these new magnetic field lines to oppose the change. So it's a pretty fascinating process, and this whole thing is called Lenz's law. Now keep in mind, the new magnetic field doesn't always go with the original magnetic field. Like if all of a sudden my magnetic field got stronger, my new magnetic field would oppose that increase, and my new magnetic field lines would actually go in the opposite direction. But the key is that whenever you have a magnetic field, a changing magnetic field near a wire is just going to create an electric current that opposes the change. Okay, so that's kind of like the end result. A changing magnetic field near a wire creates a current in the wire. That opposes the change in the magnetic field. Whoops, I still can't spell, guys. So that opposes the change in the magnetic field. And there are so many applications, and the biggest application you guys are going to see is that this is essentially how we generate almost all of our electricity. We have some kind of a relative change of our magnetic field near a coil of wire. That change causes electrons to move in the wire, and it generates electricity of us. And the strength of that new current is dependent on how quickly that magnetic field is changing, how much wire is exposed to the changing magnetic field, and the size of that changing magnetic field. And so when you guys do the virtual lab, it's going to kind of have you look at those different aspects of changing a magnetic field near a coil of wire.